This is Algebra 1, Term 4, Lesson 14, How Big is the Box? We'll be looking at a classic optimization problem in Desmos Classroom. We'll revisit a similar problem in Polypad, in GeoGebra, and at the end the students will create their own box problem. So let's start with Desmos. So in the Desmos activity, you can expect to spend about a third to half of your time. So let's go ahead and start on screen 1. The first thing they're going to do is just sketch it. You have been given these 3 instructions to build a box. The box must have a height of precisely 6 inches. The bottom of the box must be a rectangle, and the perimeter of the bottom must be 32 inches. Can you sketch it? And so they're going to sketch this box. You are advised to pace your students throughout this lesson so that they're not looking ahead. We want them to try to do this without looking at the images that come next. Okay, here's a picture of a potential box, and there are many possible dimensions for this box. There are multiple ways to create this box, but still fulfill the requirements 1, 2, and 3 that are listed. They will fill in the table with missing measurements for 4 different types of boxes here. There's no direction about how to enter those into this table, so they may not be arranged in any pattern, and that's fine. Now when they get to this screen, they're going to create an equation using x and y. And we know the perimeter must be exactly 32. They can type this equation in here as an explicit equation. They are not required to have y as a function of x. So that would be okay. In fact, it would be kind of good if kids are approaching this differently, so we can kind of point out that there's not just one way to write the equation relating x, y, and the perimeter of 32. There's actually several different equations that would all give the same line. So encourage that. One equation might have 32 in it, and another might have just half that much in it, and another might be in slope-intercept form. We might have one in standard form. So I think I've even seen a perimeter formula with parentheses in it. So I mean, you could even use that. That would be kind of cool here to explore all the different ways of representing that. They are asked to give the domain of their functions in curly brackets. So even if their equation is not written y equals, they can still restrict the domain and should do that in this problem. Be sure to refer to this teacher moves. There's quite a few notes in here to help you with this task. So the next thing we're going to do is look at the volume of the box. We still have the same requirements. How do you find the volume? I would pause and let the kids come up with some strategies for finding volume. They may remember the formula from middle school. In this table, they will go ahead and fill out their lengths. And here is where they will need to write an expression for their length as a function of x. In other words, it does need to have the y on one side and the expression on the other at this point. So they didn't have to do that when they created their graph earlier, but they will need to do that here to write an expression for length. And then finally, they'll use that expression in the width and the height to create an equation or a function equation for our volume of the box. Here they're doing some analysis of their volume. Will the volumes continue to increase forever? What do you think? And then here they will actually put in their volume function that they created with their table, and then they will use this graph to find the maximum volume. We want to know the width of the box that will produce the maximum volume and label that point on the graph with the answer. And then here are 3 different equations. Oh no, another box. This time we want a height of 8 inches, so that's a change, and the perimeter of the base is 24. So which of these equations would fit this new scenario? And then finally, we're going to talk a little bit about the intercepts, which actually are like limits in this situation. They can't really have a width of 0 inches, can they? Could we have that? What would the box look like? If they aren't sure what this is talking about, we're about to do an activity in GeoGebra where they can physically see this. It's going to show on the screen exactly what that would look like if you had a width of 0 inches. And can you have a length of 0 inches? No. So this is going to help us restrict our domain to fit the context. And so that's important. I do usually include the 0 in the graph, but I use an open endpoint at that point to show that there's a hole there that can't really be that. But I do go ahead and put it in the graph, and I encourage students to put it in the graph so that they can see what it would be if you could have 0. Where would it cross the x-axis? And what is happening there? Now, the first thing they're going to do in slides is a polypad task, and this is kind of directing them in a whole different way to look at this box problem. In the last problem, we were given a perimeter of the base. But in this problem, they're given the length and the width of the piece of cardboard, 16 by 12, and they're going to cut out the 4 corners, and this one's giving them an exact number to cut out, 3 by 3 squares. And they have to figure out the new length and width, and they're going to put those numbers here, and they're going to fold this up. Now, if you click on this, they can unfold it and fold it, and I would encourage them to do that to get their mind wrapped around this box. But this folded box is what we're looking at. What would be the length of this folded box, which is this side? What would be this width? And what would be this height? So they need to kind of look at this and look at this and this one over here and try to make sense of the length, width, and height. And then they can just simply multiply the length times the width to get the area of the base times the height, and all of that gives them the volume. What's cool about this is when they type these numbers in, they will get a little green box and a check mark to show that they do have it correct. And when they get all of these filled in, including these 4 over here, they'll get confetti on their screen. And if they're quick, they can take a screen capture with the confetti in it and put that on their slide. But the confetti goes away pretty quick, so you may not see any confetti in their screenshots. But that's all they're doing here. They're just getting their mind wrapped around this scenario because we're going to do more with that in the next activity. Once they finish that, they'll just take a screenshot of the entire thing completed and put it here on this slide, and then they'll move on to their GeoGebra task. Now this time, we're going to go to GeoGebra, and we're going to use this box, and it's basically the same scenario. But this time, they can adjust the lengths of the sides of those little squares that are being folded up. Now it doesn't fold it all the way up, so they can fold it, put it all the way down at 0 degrees, means it's not folded. This is partially folded at some degree between 0 and 90, and they can fold it all the way up to 90 degrees. So this is just helping them fold their box. They are told to start with a square size of 0. So obviously at a square size of 0, there is no box. And then I think they're told to do 0.5, which you can't hit 0.5 exactly, unfortunately, but you can kind of see what it looks like. It's kind of a flat tray. And then they can go to 1, and then they'll go to 1.5, and you can't get these exact, but it's okay. Just get close. They just need the general shape of the box to see what it's doing, and then they're going to go back to their slides. If you know the side length for the square that's being cut out, then the next thing you want to figure out is the area of the base based on that. Now, if they had not already noticed while they were in their last task, this actually does a better job of it. In Polypad, you were taking the length and they had to take away 2 of those squares to get the new width. The width and the new width. And here they had to take away 2 squares and get the new width. The area of the base would be this length times this width. So it would be this number, whatever that is, times this number. So they're using that same idea on their slides. So start with a 0. What would the area of the base be? Well, that would be actually the full, complete piece of paper that you were given. It doesn't show it clearly, so let me show you where that is. If you go all the way back up to the top, it tells you there's an 8-inch by 6-inch rectangular cardboard. So if they start with 0, that's telling you they've got 8 by 6 for the base. So you have a base, but you have no height. So you have no box really. But so your area would just be the area of that piece of cardboard. So that's pretty easy. But when you go ahead and cut out an inch or half an inch, let's do half an inch. Like, oh good, I hit it. If you cut out an inch, how much is left here and how much is left here? So take your time with these. Honestly, I would probably have kids coming up and doing this. And if you want, what you can do is give everybody grid paper and give them 1/2 centimeter grid paper. They can actually create these boxes, cut out their corners, count the squares, and actually do it. So this would be a fantastic activity for hands-on work with actual grid paper, and I absolutely have done that. In fact, I'll show you a picture of a similar activity I've done in the past. Here's an example of this task being done with a different sized cardboard, but it's the same idea of taking squares out of the corner. And what I did is I had teams create these squares and bring them up to me, and then I put the numbers inside. But I did label the width of the square inside the actual box, which is really just a paper tray because they used grid paper to make these. But they could see the volumes. And one thing we did, a total different approach to this, is they predicted the one they thought was biggest before we started, and then we actually did the calculations, and we figured out who was closest to the biggest. But this is what it looks like if you have them actually do it with paper, and it is a pretty fun task. So if you want to add that in as an additional part of this assignment, that would be a fun activity. Okay, once they've done that with 0.5, they're going to do it again with 1, then they're going to do it again with 1.5, and they may or may not be able to get the model at GeoGebra to hit the numbers exactly, but tell them not to stress out about that. Just get as close as you can to get an idea of what it's doing, and then use the actual number in the table to figure out how much is left for the length, how much is left for the width, and what's the length times the width to get the area of the base. And once they filled in all of these values, then they can come up with an equation to fit their function. They have the option of doing regression equations at this point, so encourage it, but they don't really need to. They can use just expressions with factors in there. They know the zeros of the function, so they should be able to do it that way. You may have some kids that do the vertex form for this function. That's fine too. There's actually multiple ways to write this, and we want to encourage that. Once they've written an equation and they've graphed this function, they do need to restrict their domain to fit the context. I generally do go ahead and include the endpoints and just, like I said, change the endpoints into open circles so that they don't show on the graph. But I sometimes include them so that I can click on them and see the number there. Because if you take them out of your domain in your actual graph, sometimes you can't click on those numbers to see them. And then finally, I want them to describe what's happening. Is your function increasing or decreasing? Where is it increasing? Where is it decreasing? What is the vertex? What does it represent? What happens at the intercepts? What does that look like? Well, the first intercept, I think, is where you have just the piece of cardboard and no box at all. And the last intercept is where you have no width at all. I mean, the side of the square eats up the entire box, so you don't have any width at all. And then how would you classify this function? What is it? Which function family is this part of? Then they're going to continue on and create the volume of the box. Well, they already know the area of the base because they just found it on the previous slide. So they're simply going to multiply those values by these values to get the volume. And they're going to put that here in this table. And then they're going to create another graph of their function. I will go ahead and give you all of the details for this in your teacher slide. So just take a look at those if you're not sure of the different ways they might do this problem. And then finally, describe the rate of change. Is the graph increasing and decreasing? And something else you might want to look closer at, is this graph symmetric over its domain? Because that's something we haven't really talked about before. We've not had one that looks quite like this one. And how do you classify this function? Well, this happens to be a cubic function, so this is the first time they've seen that. This is not one of the function families they necessarily need to know that much about yet. It's going to be revisited in their Algebra 2 class, but it does show them that that polynomial that they discovered in their last assignment does actually have a purpose. It does model the volume of a box in this scenario. I do ask them for the maximum point. This is not a vertex, and you might want to talk about that as a class. And then describe what they reveal in this context, the domain, the intercepts, the maximum point, and all that. And they'll just type here. This text will shrink as they type, so it's not a lot of space there, but it'll kind of grow with them as they type. So they're also welcome to shrink their text, move it around. My students, I told them a lot, don't hesitate to shrink the text down and move it over, get it out of your way, so that you can use the slide and put it on there, put your stuff on there in the way that you want to. And then finally, they're going to create their own box. They do need to choose a unit of measure, inches, centimeters, yards, feet, etc. Any unit is fine. Determine a fixed perimeter for the base of the box. So we are actually going back to the one in the Desmos activity here. Sketch the box. You can use GeoGebra or PolyPad to help with the sketch, so they could go ahead and create it in GeoGebra maybe and screen capture it and put it in here. Or one that's similar, it won't be the same. Determine a fixed height for their box. Create a function for the length in terms of the width, and create another function for the volume in terms of the width. And then graph the volume function. Restrict the domain to fit this context. So you don't want a negative volume anywhere. You want to make sure you stay in the first quadrant. Identify the vertex and the intercepts of the volume function and explain what they reveal in this context. And all of their work will actually go on the next slide. So I gave them a full slide to put their work because there's quite a bit going on here. And they should have a graph, and they should have two equations, and they should have everything labeled. Most of my students would just put everything in their graph and label it in there with text. So they would put a point for the vertex, and for the label on the vertex, they would put the ordered pair again, and then they'd put some words describing what those numbers mean. Same for their zeros. They would put the point on the graph, maybe an open circle, because you don't really have endpoints on this one, and they could describe what's happening there. And then finally, they just insert it on the next slide. Oh yeah, and they can take screenshots of their equations for their length and their volume with the restricted domain. And that concludes our last lesson for Term 4. Next time, we'll be taking our Term 4 exam. Y'all have a great day.